All right, recording is rolling. Welcome to Monday, October 9th. All right, so you guys know first night weeks is ending in a few days. You guys know that? Check focused for any NTIs that would be not turned in. Once this closes, there's nothing I can do about that. It's actually closed over the weekend. Teachers have a few days. Right? Guys, I have not handed back your forces quizzes yet because I'm still waiting on a few of those to come in. Right. So we'll hopefully get those really soon so I can get those back to you guys so you can do corrections before the 9 weeks is over. It's gotta be real soon here. All right. So how this section is organized, different textbooks do it differently. I'm gonna start universal gravitation with you guys Wednesday. That's like the kind of the second half of this. Later on today, we'll start with some of these textbook questions and how your textbook organizes the stuff. Here is like the first half of chapter 6 is projectiles, which we did a few weeks ago, so we're past that. The second half of chapter 6 is the circular motion, centripetal force, and then chapter 7 is universal gravitation. So what we're really kind of in the middle of doing is wrapping up the second half of chapter 6, and then we're going to start chapter 7 type on Wednesday. All right. Oh, and then don't worry about AP because that's not you guys. All right. So I do have a starter question here. Has something to do with this O'Neill cylinder. Did I show you guys about a week or two back? It was a clip from a movie from the 1960s called 2001: Space Odyssey. They had a giant space wheel that was spinning, right? And if you're inside that space wheel, even though there's no like gravity field from a planet, if this wheel is big enough and you're walking around the inside, it might be hard to distinguish between this normal force provided by the wall and like actual gravitational field, right? So if you knew how big this was, supposed to give you 1 kilometer diameter, I wonder how fast would this have to rotate, right? And then how much time would it take to rotate once in that case? Hey guys, everybody look up here? You guys taking notes? You guys taking notes, right? Right. All right. So think of it as a review of last few things you guys saw back last week, right? Whoops. You guys had a simpler version of that. Here we go. Okay. So you guys did this lab back last week where you had like some mass in a circle of some radial size going to some speed balanced by where there's some hanging weight down here, which was effectively providing a tension force to act as a centripetal force. And you guys came up with this as the solution. I split you guys up into 3 experimental groups. One of the groups was what if you change out the swinging mass? How does that affect the speed for constant R and constant weight, right? And this particular relationship, you guys found there's a direct relationship between the square of the speed and the reciprocal of the mass that lined up in a straight line, right? There were a couple of experiments too. That was one of them. Right, anyway, we came to this conclusion. Right? If you divide through by the point mass, then you get the centripetal acceleration, right? Which is also directed inward towards the center. Centripetal anything always pulls to the center, pushes to the center, right? But hey, these two are Newton's second law of motion away from each other, right? Now, I was having you guys assume pretty much a flat circle. Technically, it was a little bit different from that. It was a little bit simplified because there's always some vertical component for the weight, right? Here, guys, look up here. You guys taking notes? You guys got notes out, right? Got notes, right? Right. So, if this weight was significant enough or you were swinging around slowly enough, then maybe the fact that it actually was a conical pendulum would start to matter. It was like a cone shape. You guys say like a cone shape, right? Right. But it probably hardly made any difference. So if you just simplified it to be like this, it was plenty good enough, right? But what if this angle from the vertical was significantly less than 90 degrees, right? Oh, let's look at big picture. Like, how would you take that into account? Because one of the textbook questions we're going to look at yesterday, that's actually on deck pretty soon, is going to involve something about like this. Okay. So in that case, the tension in the string would actually be greater than the centripetal force. See, what you could do, there are 2 forces that are acting on this point mass here, 2 forces. It's weight acting straight down, and that tension in the string, which is pulling up kind of up and to the left. Right? And now up and to the left is doing 2 things. It's going up and it's going to the left. Now the up component, if you break it into components, do you guys see a nice right triangle here? Right triangle? It's kind of like perspective, right? perspective, right? This upward component is exactly balancing the weight down. You guys see it? This dashed up balances that weight down, right? Ooh, that's like this condition right here. This is like the sum of the forces vertically goes to 0. And there would be 0 vertical force because this point is not going up or down. Right? But it is on a curved path horizontally. So there is a net horizontal force. In fact, that net horizontal force is the centripetal force. Right? In terms of the tension in the string, it'd be the sine component playing off this angle from the vertical. Now you guys were assuming that the tension was basically horizontal. But that aside, if you look at this being like a cone, play off the sine of this angle, sine of whatever this angle is, right? Because you got right triangle here. Right? This would be the net force, and that net force is your mv squared over r. That's what that is. Okay, you guys got? Okay. If you like it, you can think of it this way. If you put these two forces, there are only two forces on this point mass, the actual tension and the weight. If you add those together tip to tail, right, like vector addition, either way you'll get this net force. I could take this weight and slide it up here, tip to tail that, or I could take this tension and slide it, tip to tail this weight. Either way, I'm going to get one of those dash paths so I get a net force like that. Okay, and so hold on to the idea. You guys will see that later. Okay, but a more immediate application here has to do with ooh, look at there, O'Neill cylinder. Right now, what are these expressions down here at the bottom? Right, because if you want to figure out something about like how, here, what would I even come up with a different type of expression for O'Neill cylinder rather than just use like straight up what you guys got in your lab, right? Well, let's walk through the story. So these guys walking around the outside of this O'Neill cylinder, right, that's spinning at some rate. Right? What if there's a ladder that goes up through the diameter? Is this ladder? Actually, let's look at the poster version because the poster version is bigger. It's easier to see. Right? But this guy is climbing this ladder. Right? What is this guy going to feel like when he gets to the middle of the ladder, which happens to be right on this axis of rotation? Is his dashed line axis of rotation? Right? What would this guy feel like right at the center? Really heavy or really light? I think really light. I think if this guy like pushes off and let's go to the rungs of the ladder, I think he's just gonna float off into space. Right? He would feel weightless. Right? He would feel weightless right at the middle. Right? And if he's climbing back down the ladder, or this whole thing's rotating, right? I bet he feels heavier until he gets down to the base of the ladder. Right? And now if you spin this at just the right rate, I bet all these people can feel like Earth gravity, 9.8 meters per second squared. Right? Right? Okay, so this centripetal acceleration would then depend on like where you were standing, right? But this whole O'Neill cylinder is turning at the same angular velocity. That's what this omega is, right? This curly W looking character, right? It's like the same revolutions per minute, except we'll call it radians per second would be our unit. Right? So whenever you have something like that, like a turntable or like a rigid disk that's all rotating at the same rate, a lot of times it's more convenient to think in terms of some kind of angular velocity rather than some linear velocity. Right? Like your guys' point mass from your lab, that was a linear velocity, meters per second. But there's all different linear velocity all along this ladder. Okay, so we're going to think about this in terms of angular velocity. So what's the connection? Well, let's do a little bit of a review here too, because I know you guys haven't seen this in a few days. Okay? So we used to have this linear motion. Now we got this rotational motion, sometimes called like angular, this or that. Right? Instead of saying how fast meters per second, now I want to know like how fast is it rotating, like radians per second. Sometimes it might say revolutions per minute, same concept, right? And the connection there is this right here. You guys remember I had these 3 Roosevelts on a turntable? And I don't have the turntable in front of me right now, but here, this could be my 3 Roosevelts right here. Right? There was one right in the center. He wasn't going anywhere, and he wasn't going any speed. But the whole turntable is turning at some omega, right? And the further out you are, the faster you're going. Like if I point a radar gun at this guy, or point a radar gun at this guy's going to clock faster than this guy. Because it's like twice as far out in terms of radial distance, right? Right? You can take this expression right here, V equals omega r, and substitute it into this V right here. Actually, let's do this one. Let's do the acceleration version. Okay? And you can get the centripetal force or centripetal acceleration for, say, like a rotating turntable or O'Neill cylinder. So let's try that. Let's see what that looks like. So we'll start with your guys' conclusion from your lab. Centripetal force is mv squared over r, where the m is like the point mass in the circle, or like any one of these guys walking around. Okay. But I'm going to substitute for where the v used to go, I'm going to substitute omega times r, because that's what I just showed you from that poster, right? So that whole expression gets squared, or that little piece gets squared, right? And I just substituted in that right there. That's what I substituted in. Okay. Linear speed is angular speed times the radial distance. Okay. Ooh, that r is that r. Guys, what is r squared divided by r? Just find r, isn't it? Right? So m times omega squared times r. Ooh, something kind of interesting to notice here is that how does the centripetal force relate to the radius? Well, as a point mass, it's like inversely related to the radius, right? There's an inverse relationship here. But if you think about it like as a rigid disk, like as a rigid disk, actually that centripetal force is directly proportional to the radius. Like if you're climbing this ladder or moving down this ladder, right? That almost seems like paradoxical. Now, it does make sense if you sit down and think about it deeply, but it's just something you have to do. It's just how to kind of sit down and think about it deeply. Like, wow, wait, is it directly proportional or inversely proportional? Well, it kind of depends on, is it a ball on a string or like a solid disk? It kind of depends how you think of it there. Right. Anyway, I can divide both sides by the mass, like Newton's second law of motion, and get centripetal acceleration, which is just omega squared times r, right? And guys, which direction does centripetal force, centripetal acceleration always point? Towards the what? Towards the center, right? Because suppose this thing's rotating, and then the walls just kind of like fall away. Like, okay, doesn't each one of these individual people just fly off tangent to their motion, right? So put the walls back. What's preventing them from doing that? Which is like Newton's first law of motion says they all want to fly off tangent to their motion. That's Newton's first law. So you put the walls there. It's a normal force from the wall that's pushing them into a circle. That's preventing them from flying off into space tangent to the motion, right? So the normal force in this case is providing the centripetal force, right? But we're interested in centripetal acceleration, right? So let's go back to the setup here, right? So something about we're targeting Earth gravity, 9.8 meters per second squared. We want all these people to like close their eyes and think that they're on Earth, right? Oh, and I told you how big the cylinder was. I said 1 kilometer diameter, right? So here, let's get this on the board. Centripetal acceleration is omega squared times r. Right? Now the question is the time period, how much time to go around once. I don't see anything exactly about time here, but I bet it's related to this omega. So about turns per time. Ooh, right? Let's go ahead and solve for this omega. You guys think we should do that first? Right? Right. Oh, and guys, what number goes right here? 9.8 meters per second squared, right? Because that centripetal force divided by the mass is centripetal acceleration, right? We want them to feel like they're in Earth gravity. Right? And what number goes right here for radius? 0.5 kilometers, right? Right. Now, if everything is in base SI units, then what number goes into your calculator for that value? Not 0.5, but because you don't want kilometers, you want 500 meters, right? 500 meters, right? Because 0.5 kilometers would be 500 meters, wouldn't it? Yeah. So we're gonna go 9.8 meters per second squared right there. We're gonna so right there, and then 500 meters goes right there, right? By the way, if you guys can ever beat me to the answer, you guys know I always encourage you to beat me to the answer, right? So I'm trying to go a little bit slow to give you guys a chance to do that. If you can beat me to the answer, then good indication you know how to solve this stuff, right? Okay. I could solve in terms of variables, or I could solve in terms of numbers. If I solve in terms of variables, I've got omega squared equals AC on R. So omega is the square root of AC on R, right? To solve in terms of numbers, I got omega squared is 9.8 on 500, and a bunch of units, meters per second squared, meters, right? So omega is the square root of that. $500 meters, meters per radius, however you like to think of that. Right? Right. So calculator time. Calculator square root of that on that. Okay. I'm looking at this many. What unit, guys? That's 0.14. What's the unit? How do you here? Angular velocity is something about how fast it's turning, right? I don't see any sine, cosine, or tangent. I just plug it straight into an expression. So there's only one unit this could possibly be. Is it revolutions per minute? Is it radians per second? Radians per second, right? Okay. So that's how fast this whole O'Neill cylinder is rotating, right? 0.14 radians per second. So that everyone feels 9.8 meters per second squared artificial gravity field, right? But the question is actually, how much time does it take? How much time, right? So we need to do one more thing with this. Okay. You could use a formula for this. I bet you could use some version of like theta equals omega times t, solve for t, right? So t would be what? Theta on omega. Oops, theta on omega. Anyway, I'm going to do a unit conversion, like dimensional analysis version of this. It's a little bit different way to think about it. Okay. So I'm targeting one revolution, and I want to convert that into how much time does it take, right? So let's go through a few conversion steps. What's my next conversion step?
Radians.
Yeah, radians, right? So how many radians per revolution? Huh? 2 pi? 2 pi radians is equivalent to 1 revolution, right? Like you guys remember here, what I told you guys last week is you probably know this since like 5th grade. You guys know circumference equals 2 pi r. Now that's one specific version of this. Okay, so that would be 1 revolution, wouldn't it? So for one circumference equals 2 pi r, right? So 1 revolution is 2 pi radians, right? And now we can bring in how many radians per second this is. So 0.14. Oh, I should have asked you guys, just a 0.14 go on top or bottom. How do you know to put it on the bottom?
That's last time.
How about, because radians here, seconds here. Okay. Yeah, so time ends up on the top, and the radians cancel out on the bottom. Right. Let's put it all together. What's 2 pi divided by 0.14? Right. I got 44.9. The unit is seconds. I call it about 45 seconds. Right, 45 seconds. Okay, is that? Okay. So in the future, when we eventually start building these O'Neill cylinders, suppose like, I don't know, 500 years from now, and there's an O'Neill cylinder's face has a diameter of 1 kilometer, right? You can pretty well know that it's going to take about 45 seconds to go around once, so that everyone on the inside feels like they're on Earth, right? Like we're kind of biologically evolved to be in Earth gravity and the whole deal, so it's probably the healthiest gravity field to be in. Okay. Okay, guys got that? Hey, everybody good? All right. Let's look through some of these other posters. Showed you guys some of the. Oh, there's one other poster. I want to look at. Right. Actually, let me pick up from a conical pendulum. Okay. So I showed you guys this one earlier. Okay. But the next one that I show you guys is actually really similar to this one. Right. And that's the car going around the curve on a big track. Right. I think I showed you this last week, but it's probably good to see it again. Second time. Right? So here's the story with this one. Your car, you can make a turn on a flat road, right? But if you do, guys, on a flat road, what? Here, guys, you take notes. Right? What force allows you to make a turn on a flat road? Friction. It's got to be friction, right? What if you're building a road somewhere where sometimes it gets really icy in the winter, the road's iced over? Do you necessarily want to rely on friction to make the turn? That's a really iffy thing, right? But hey, what if you like bank the track, right? So we know we're making some turn, right? Anytime you guys exit the interstate, there's probably a banked road, right? Like a banked road, right? Which helps you go faster to make that turn. What if I want to make the turn with like no friction at all? Look, I drew 2 forces on this car, and neither one of them is friction, right? You can make the turn without friction. Hey, I wonder if you know what the speed limit is, and you assume the cars are going pretty close to the speed limit, and you also know what is the radius of curvature, right, of that turn. If you can calculate the angle to bank the road so that you could make a pretty safe turn even when the road is iced over, right, when there's almost no friction, right? So side by side with the conical pendulum, you guys see how that looks like nearly identical, right? There's a weight on both of them, and there's some kind of force up to the left. Now the string is a tension force that's pulling. In this case, with the car turning, it's a normal force from the road that's pushing, but geometrically they look pretty well identical, don't they? Is that so that the vertical component for each one is balancing out the weight, and the horizontal component for each one, that's what's providing the net force, which is acting as the centripetal force, right? Your mv squared over r, right? Guess that? Is that too? Right? Now, I usually tell you guys whenever you have like a block on an incline, introduce a Cartesian system that aligns to the surface, right? But I haven't actually done that here because the way I set it up here is actually easier to solve it. Right? Actually, maybe a hint for why to solve it this way specifically is to introduce a Cartesian system that aligns with gravity. I mean, right? Imagine you're driving that car, right? And you're driving pretty fast, and you're going around that turn. Do you at that moment feel really light or really heavy or the same weight as normal? Really heavy, right? You think you feel really heavy, right? I think I would, right? Feel pretty heavy, right? Which might be a hint that maybe this normal force is greater in magnitude than the weight. And it is, right? You see how I drew that a little bit longer than this? So that if you take that normal force and you break it into components that do align with the gravity field, right? How much up and how much in. Do you guys see that the vertical component balances out the weight, right? So there's zero net vertical force. So the car's not going up or down, right? But the car is turning horizontally. Right? Oh, and that's what this horizontal segment has to do with, right? How much the normal force is pushing the car into a circle, right? Now, big picture here, because there's different ways to solve this. You can use different amounts of paper for this period, but I've only got like 3 lines of writing here. Okay? Boom, 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 something like that. I can solve this thing. Okay? So big picture, you guys see it? This weight and this component of the normal force balance out. They have to match each other, right? Right. So this component of this normal force effectively is equivalent to the weight, right? Guys, that. Right. And then the horizontal component of the normal force is what is acting as the centripetal force, mv squared over r. And these two components right here of the normal force, how much up and how much in, that's like 2 legs of a right triangle. You guys, 2 legs of a right triangle always have a what relationship with each other? Sine, cosine, or tangent? Guys, 2 legs of a right triangle, is that sine, cosine, or tangent? It's tangent. It's always tangent, right? So you could say tangent of this angle theta, which by the way matches this angle theta. They're same theta, right? Right, same angle. So you can say tangent of theta is this divided by this, opposite over adjacent. Or you could rearrange that and say, hey, if I take this vertical leg, which is equivalent to the weight, and I multiply that by tangent of the angle, that will spit me out the opposite leg, which is the centripetal force. That's what this line is right here. If I take the leg that's equivalent to the weight, so I'll just call it the weight, and multiply by tangent of the angle, that will tell me centripetal force. Then you can rearrange that, and you get this boxed in version right here, right? So if you know the speed limit, and you say, okay, this car's going around some speed, around a curvature of like so many meters radius, and such gravity field, you can solve for how much you need to bank the road, right? Right? Just take inverse tan on both sides. Right? You guys see that? All right. So that's the last main posters so far. Got some other posters for gravitation. We'll probably save for Wednesday. All right, let's do some of your textbook puzzles. You guys ready for textbook puzzles? Textbook puzzle time. All right, so we got lined up here. All right, so latter half of chapter 6. Number 61. Oh, so just like normal, just the ones that are circled, I'm gonna have you guys turned in. Got some extra ones for extra practice if you like. Car racing, 61, car racing. A so many kilogram car completes 1 loop in so many seconds around a circular track of such radius. Car moves at a constant speed, right? Now, you guys know at this point in the class that constant speed and constant velocity are 2 different things. Is this car constant velocity? No, because he's always making a turn. He's on a curved path. Constant speed means the speedometer needle is like just constant value, right? What is the acceleration of the car? And guys, what kind of acceleration are they talking about? Is that a linear acceleration or a centripetal acceleration? Centripetal, right? Because he's on a curved path, there must be a centripetal acceleration. In fact, I know there's zero linear acceleration because it's constant speed. She's not speeding up or slowing down. Right? Okay, and then there's a follow-up question, but let's do first one first. Okay. 61. Car racing. Let's get circular track going on. Circular track. Okay. I'm going to use numbers that are a little bit different from your textbook values. Okay. I'll have a mass of, say, 700 kilograms. Let's have a radius of about 60 meters. And let's say the time period for one revolution is about 19 seconds. Okay, so numbers a little bit different from your textbook value, but not crazy different, right? Right. So first question was, what's the acceleration of the car? And of course, it's going to be centripetal acceleration. So we should probably break out. What do you guys think? What expression should I write right here for centripetal acceleration? Should I do v squared over r? Right? Yeah, that would do it, right? Right. I never actually did anything with the mass of the car. Interesting. I probably don't need that, right? If I want to know the force on the road or something. Okay. All right. Well, okay. Well, I know what the radius is because that was given in the textbook. So just pop that in right there. Right. But what's the speed of the car? Ooh. Hey, do you guys know a way that you could find the speed of the car? I bet it's the same way that you did it in your lab a few days ago. Right? Right? Guys, speed. Is speed distance divided by time? Right? So distance divided by time. You can call that maybe circumference and time period. Right? Those could align with each other. There's one circumference and one time period. Right? Is that like t pi r divided by t? Is that what that would be? Oh, that is exactly what you guys did back in your lab a few days ago. Right? That's how you guys figured out the speed. You're doing the same thing right here. So 2 pi times the radius of curvature, so many meters. That all happened in so many seconds. Oh, look, I'm getting meters per second. Hey, that would be like a speed. What is that times that divided by that? Okay. I'm looking at, that's literally 1984 meters per second. Those numbers. So there's the speed of the car. Right? No, it's not quite the answer yet, but that's an important middle step. Right? All right, now what? Okay, well, let's go back to this expression centripetal acceleration, because now we can take this value and pop it in right there. Is that what's about to happen? Okay. So centripetal acceleration is 1984 meters per second. Square that, divide by 60 meter radius. Right? Let's go with the units. Meters squared per second squared divided by meters. Is that like meters per second squared? Hey, that would be an acceleration. Square that, divide by that. That's like this many meters per second squared. Right? That's the magnitude of that acceleration. The other part of any vector quantity is direction. Right? Guys, this is towards what? Toward the center, right? This is like a center-seeking acceleration, right? Side note here, how many G's is that about? Is that about 6 or 7 G's, you guys think? Right, and I'm so sorry, about 0.6 or 0.7 G's, that's what I meant to say, right? It's just divided by 10 meters per second squared, right, per G. So that's over half a G of just lateral, right? You can do Pythagorean theorem if you wanted to, right? How much down is being pulled, how much left is being pulled, right? What's the other question there? Oh, what force? Okay, so this is question B. That was question A we just answered. Okay. Question B, what force must the track exert on the tires to produce this acceleration? What force? Right? So here's where maybe the mass of the car matters. But force. So do you guys say centripetal force is mass times centripetal acceleration? Okay. So I've got a so many kilogram car, this many meters per second squared acceleration. That many newtons, and then it gets like toward the center, or the center of the circle, right? Something like that. Actually, there's a different way you could interpret that question too. Say like, what type of force are we talking about? Okay. And then, well, it depends on something about what kind of track are we talking about? Because if we're talking about a flat track, what's the only kind of force that could be? Like a friction force, right? Oh, but what if there is no friction? Do you guys think we could calculate how much you have to break the road? Right. So I could say if flat track, then the friction force is providing centripetal force, right? But so friction force is centripetal force if the track is flat, right? But what if no friction? So if no friction, then how much to bank the road? Okay. Right. What is that angle? Right. So let's figure that out because your book's not asking that, but that could be a fun side quest here. Okay. So suppose there is no friction, right? And the car's still going around that curve. Right? How much do you have to bank the road? Right? Well, set that up right here. Right? Walk you guys through this. So well, let's do derivation real fast, right? You know, normal force times cosine of the angle is equivalent to the weight. You know, normal force times sine of this angle. Remember, this angle are a match, right? Right. That's centripetal force. And for these two guys, tangent relationship. Got this setup right here. So it comes to this, algebra shuffle, get this. Right. Let's go ahead and just take it from that point. Let's go v squared over gr is tan theta. Okay. Remember that the mass of the car actually cancels out through this process, right? So even if you had little cars, big cars, whatever, right? They could all be going at the same speed around this curve. Okay. Ooh, could I just take the inverse tan of both sides? Can I just do that? Right, so theta is inverse tan v squared over gr, like that. Okay. So what would that be? Inverse tan. Okay. Well, I know the speed of the car was 1984 meters per second. So square that, divide by, let's call it about 10 meters per second squared gravity field. And then radius of curvature, did I say, I feel like I said 60 meters. There we go. Yeah, I went with 60 meter radius track. Right, like that? Sure. And so it's inverse tan of that squared divided by that. Okay. I'm looking at, 33 degrees from the horizontal. All right, so I need to bank that road at a 33-degree angle. If I think all the cars are going around at that speed, right? And I want them to be able to make the turn, even if the road is iced over. Okay. '62, hammer throw. Athlete whirls so many kilograms hammer, so many meters from the axis of rotation in a horizontal circle. Okay, just so we're helicopter view looking straight down the sky. The hammer makes one revolution every so many seconds. what is the centripetal acceleration of the hammer, and what's the tension in the chain? Okay. This looks a lot like your guys' lab last week. So we'll do two little bit different perspectives on this one. Right? We got some numbers on the board here. Number 62. Right? I'll say the mass of my hammer is, I'll go with 6 kilograms. Your book went with 7. I'll have my radius of curvature be like 2.1 meters. Your book has a little bit less than that. Right? Let's say the time period to go around is, they want 1 second. I'll go 1.1 seconds. How about that? Make it a little bit different from the book, but not crazy different. Okay. What's the centripetal acceleration, and then what's the tension? Okay. So centripetal acceleration, I know centripetal acceleration is like v squared over r. Right? Ooh, I think we're going to run into the same thing that we ran into with the cargo around the track, right? Which is that we have the r. We just pop that in. Right? But the v, can v just be 2 pi r divided by t? Right? Can I do that? Right. So we got to get v first. So v is 1 revolution in 1 time period, because it went that far in that much time. Okay, so now I can get the speed, right? Get the speed. So let's do 2 pi times this many meters radius, all divided by this many seconds it happens in. Get many meters per second is that. Right. That's like, almost 12 seconds exactly. It's like 11.995. Right, let's go 12 seconds. Sorry, 12 meters per second. 12 meters per second. Okay. And take that and pop that in right there. Right. Right. Okay, so we're done. Pick up here. So centripetal acceleration, v squared over r. Okay, that's going to be 12 meters per second. It's going around. Square that. Divided by radius of curvature of so many meters. No, sorry. Gotta change that. I was calling it this many meters. There we go. Like that many meters, right? All right. So what is this? Square that, divide by that. Okay. I'm looking at, this many. That's meters per second squared is what it comes out to. There's your centripetal acceleration. Right? Suppose there's a ladybug that lands on a hammer and then starts flying around. How many G's is that right there? Nearest whole number. There you go. Yeah, 6.87 G's, about somewhere there. Right? And that's just lateral, right? That's just, right? But there's also the added effect of the actual weight, right? This is just like how much one number. Right? That's kind of related to your next question. What's the tension in the chain? Now here's where I'll show you guys two different perspectives, and the fact that they're not going to differ a whole lot. Okay. When you guys did the lab version of this, because this is basically your lab, right? Or the setup, right? You guys came up with this, right? And the tension in the string was equivalent to the hang weight. Is how you guys got that, right? I had you guys assume basically a flat circle, right? But if you really wanted to get more technical about it, you could say, well, it's kind of a flat cone, right? So maybe it's more like this type shape, right? In fact, it was like, if it was a really pronounced cone, right? If you had a really heavy mass here and you're going around kind of slow, right? Maybe it would look more and more like this than an actual flat circle. Right? So let's do both perspectives. Here's the simplified version, and here's the more realistic version. Right? So the simplified and the realistic version. Right? What would the tension in the chain be? Right? So the centripetal force, you could say, would be the tension of the chain if it was all a flat circle. Wouldn't that just be mass times centripetal acceleration? The hammer was so many kilograms. So many kilograms was the hammer. So many meters per second squared is the centripetal acceleration. Put that all together, I'm getting this many newtons. Okay, that many newtons is the centripetal force. That's the centripetal force, right? Okay. Now that's where you guys did a simplification on your lab last week. You said, well, the centripetal force is the tension in the string, call it a day. Right? What I do here, though, is say, well, how different is that from the actual tension in the chain? Because the actual tension of the chain, I bet, is going to be a little bit bigger than that. And to get that, I have to think about this being actual, like, cone shape, right? So here's the hammer. It's got some weight. It's got the, I'll call it F sub T, the actual tension force. Right? For that tension force, you can break into components. Okay, I didn't draw this exactly to scale. Okay. But the amount the tension pulls upward balances with the weight down. Right? And the amount that it pulls inward is the centripetal force. Okay. So here, slide this around. F sub C is what this is, right? So this is equivalent to the mg here, right? Can I do FC squared plus mg squared, take the square root? I could just Pythagorean theorem this thing, right? Pythagorean theorem. Okay. If I'm solving for what is the tension force, the actual tension force. That's like actual. You do Pythagorean theorem. It's the square root of the weight squared plus centripetal force squared. Right? You like that? Okay. So with some numbers thrown in here, well, the mass of my hammer was 6 kilograms. So guys, what's the weight of my hammer? Is that going to be 60 newtons, right? Right, so I got a 60 Newton weight hammer. Centripetal force, I got is 411 newtons. Like that, right? You guys okay with where I'm getting these numbers? Yeah. Right. Okay, here. Back up and do a little bit of a review here. Okay. Right. So, you guys' lab last week, you guys had this going on. Right? But if you really think about it, this could never be exactly a flat horizontal circle exactly, right? It's always going to be like some version of this cone, right? Where the string's like pulling kind of up into it, right? Because it also has to support the weight of the mass that's going around at the same time, right? Now, if it was kind of a light mass or you're swinging around pretty fast, you could probably take this and simplify it and make it look more like this, right? But realistically, it's some version of a cone, right? But it's probably not crazy different. And that's one thing I want you guys to see. We haven't quite got to the answer yet, but when you guys see the answer, say, okay, well, it's not a whole lot different. Okay? And so how much different is going to be? Right? Right. So here we got a hammer going around a circle on a chain that has some tension in it, calling F sub T like a tension force, tension in the chain. Right? Now, if you just stop at the 411 newtons for the actual centripetal force, that's probably pretty close to the tension, but not exactly. Because the chain isn't just providing a centripetal force, it's also holding up the weight at the same time. Right? And those two are at right angles to each other. That's vertical versus horizontal, which means you can add them together with Pythagorean theorem. So how much up does it pull? Well, that's like the weight of the hammer, 60 newtons. How much in does it pull? Well, that's the centripetal force, which we found to be 411 newtons. Right? So what's the actual tension in the chain? Right? I bet it's going to be a little over 411 newtons, but probably not a crazy lot more. Well, let's figure out exactly. So what is the square root of that squared plus that squared? It's like, yeah, it's like 415 newtons. I see that? Right? So what's the actual tension of the chain? It's not 411 newtons, it's 415 newtons, which is just a little bit bigger. I mean, what is that compared to 411? That's like, it's 1% more. It's literally like 1% more, right? Right? So when you guys made that simplification in your lab last week, yeah, the numbers were different by about 1%, right? Right? Um, 65. Friction provides the force needed for a car to travel around a flat, horizontal, circular racetrack. What is the maximum speed the car can safely travel if the radius is so many meters and the coefficient of friction is some number? Okay. Ooh, yeah, you guys ever driven off the interstate? You're taking the exit, and you can feel maybe if you're going a little bit too fast, the car's like, ooh, the car's about to like slide off the track. Right? Let's talk about what we've got going on here. Right? They usually bank the road to help that not happen. Right? So if it's a flat track, ooh. Okay. Right. So I'm gonna have you guys do a lab, probably tomorrow, I'm thinking. That's gonna be, related to this idea, except it's gonna be a turntable. I'm gonna have you guys solve for the coefficient of friction. So your next lab coming up, I think tomorrow, is gonna be probably kind of similar to this one, right? A little bit different. Okay. So let's get a track going, circular track. Right, here's a car going forward. And I'm thinking there are three forces on this car. There's the weight and the normal force, which are into and out of the page for like helicopter point of view. Okay. And there's the friction force, F sub FR friction force, which is letting the car make the turn. Okay. If you look at the car from behind, here's the car from behind. Got some wheels, got a license plate, got the rear window. Okay. Here's the same three-body diagram. It's got a weight, it's got a normal force, and it's making a left-hand turn, so the friction is pushing to the left. Okay. So I want that whole three-body diagram because I know there's a relationship between this force and this force. And that relationship is the coefficient of friction, which is one of the numbers they gave us. Coefficient of static friction is greater than or equal to the friction force compared to the normal force, right? And if we're just at the breaking point, we're trying to max out the speed of this car, I could even call that equals, and I can solve it from there. Okay. So I think tomorrow we'll go ahead and finish solving this one, and then I'll show you guys how that relates to the turntable version with the lab, because we're about run out the clock today.